Hello friends, welcome to lecture number 4 of Electricity and Magnetism for BSc and MSc students. So application of Gauss law. We have already discussed how to apply this law to calculate electric field intensity due to due to spherical cell in the last lecture, in lecture number 3. Link is given in the description box. You may watch if you want. And now today we are going to discuss the same due to charged solid sphere, not spherical cell. This time we are going to consider solid sphere instead of hollow sphere, solid sphere. Okay, so please subscribe the channel if you haven't subscribed yet, and inspire me to create more videos, new contents for you. And if you think these videos are helpful, please share with your friends, hit the like button, and also hit the bell icon so that you get notified when new video will be uploaded, right? So now let's start. So here you see, suppose we have a solid sphere and enclosing charge q amount of charge of radius r. This capital R is the radius, O is the center here, and we are going to calculate electric field at point P. P may be outside. We are going to consider three cases: P outside the sphere, on the surface of the sphere, and inside the sphere. Okay, all the three cases. So now, in order to find the electric field through this P, so let me at this P, let me draw a Gaussian surface through this point P. Okay, so let me make it dotted line which represent Gaussian surface, which is again a sphere. Okay, it is spherical shape. So here is the P, and let us consider a very small area element ds. Suppose ds, and the area vector will be in this direction, and this P is at a distance of r from the center. Okay, the distance from the center O to this P is r, small r, and in this case small r is greater than capital R in this case, right, when P is outside the sphere. So this is gonna be if we consider that it encloses positive q charge, then electric field should be radially outward. This will be the direction of electric field. And area vector is always normal to the surface, right? So that's why that will be also in this direction, in the same direction along E. This is the area vector ds, which is normal to the surface element ds, right? So we can consider that way. And we can consider unit vector n cap along ds, right? So now let me write what are the things we have considered. Just wait. Okay, so here I have written what we have considered. So here you see, we have considered a solid sphere of radius capital R with center O, and rho is the volume charge density of the sphere. That means rho will be equal to the charge per unit volume. If q is the charge enclosed by the sphere, then q by 4 pi, that's gonna be 4 by 3, not only 4. Volume of a sphere is 4 by 3 pi r cube, because radius of the sphere is r, capital R, right? So that is the volume charge density, rho. So hope you have understood. So now you see, this P point is at a distance of r, so OP is equal to r, right, from the center. So that is what we have got. And suppose ds be the area vector normal to the surface element. Small surface element ds. So along E vector, and direction is radially outward. So radially outward. Let me write. Radially outward, and n cap is the unit vector along ds vector, right? So let us write that way. So case 1, so here small r is greater than capital R. That means P is outside the sphere, right? P is outside the sphere, right? And this dotted line, this dotted surface is the Gaussian surface. This dotted surface, you can see, is the Gaussian surface. And of radius r. So let me write here, Gaussian surface of radius r, small r. So let me write that way. So now let me take another slide. Now according to Gauss theorem, we get electric flux, which is given by surface integral E dot ds. E is equal to q by epsilon naught, right? Q by epsilon naught. So here dot product of E vector and ds vector, that E ds cos theta. So here this theta will be 0, right? Theta will be 0. I will write it later, right? Epsilon naught. Now we can write E surface integral ds, and cos theta will be equal to 1, right? Just we can keep it this way, since angle between theta is the angle between vector E and ds vector, which is equal to 0 degree. So cos 0 degree is 1, right? That is why we have got this relation. Now if you integrate, that means if you find the flux through this whole surface, through the total Gaussian surface, then you will get E integration of ds. We know the surface area of this Gaussian surface, which is of radius small r, will be 4 pi r square, right? So q by epsilon naught, that is what we will get, right? So here one more thing, just let me write here. Okay, so here you see, so what we have got here, integration ds, surface integration of ds, this is nothing but 4 pi r square, right? Remember that. So this is what we have got. Now from here E will be equal to electric field E will be equal to 1 by 4 pi epsilon naught into q by r square. That's what you can write. Yes, that is what you can write for small r greater than capital R, right? So this is the surface area, this is the electric field at P due to the solid sphere, right? Due to the one more thing, again we have also considered that sigma, that is not sigma, rho, that is volume charge density, that is q by its volume 4 by 3 pi r cube, right? If you use this relation here, so from here q will be equal to from this relation we will get q will be equal to 4 by 3 pi capital R cube into rho. That is what we will get. If you use this relation here instead of q, then what we will get? So just even check. Let me go to the next slide. Then what we will get? Electric field E 1 by 4 pi epsilon naught. Instead of q, we're gonna write 4 by 3 pi capital R cube rho by R square, right? So if you simplify this, here you can see clearly this 4 cancels, right? So we will get here pi also gone, so we're gonna get only E rho E is equal to rho by epsilon naught capital R cube by 3R square. That is what we will get. Okay, so you can express this one in vector form as well. E vector rho by epsilon naught, so you can write the 1 by 3 here, and capital R cube by small r cube and unit vector n cap. You can write that way also. This is vector form. This is vector form, and this is the scalar form, right? So you can write the expression this way also and this way also. This is also correct. Okay, so now what if small r is equal to capital R? That means P is on the surface of the sphere. Then what you gonna get? So just replace the capital R just replace the small r by capital R. Then E will be equal to rho epsilon naught capital R cube by 3 into capital R square, and R square cancels R cube gives electric field E is equal to rho by epsilon naught capital R by 3, capital R by 3. That is what we will get. Now let's go to the third case. If the point P lie inside the sphere, right? So that means if this point P is inside the sphere, then what we will get? Here you see, in this case this P is inside this surface. This is the solid sphere, right? And now the Gaussian surface is this. This is the Gaussian surface. Of radius smaller, which is smaller than capital R in this case now, right? Now you see, let me take this as a small surface area element ds, represented by this vector ds vector, right? D as vector, and electric field is also in the same direction, E vector. So now you see radius of this Gaussian surface is small r, right? This is small r. So here you can see. Now you see in this case, here you can see that charge enclosed by the Gaussian surface is equal to or you can say is Q is equal to volume charge density, that is rho, into the volume of the here the Gaussian surface in this case is spherical, sphere of radius r, right? Radius is small r. So volume of this Gaussian surface is equal to 4 by 3 pi small r cube, right? Now you see, let me go to the first case. So this is the first case. Here you see, let me take, this is equation number 1. This is equation number 1, this expression. Now replace this Q by this value of Q, right? So let me write the equation number 1, what we had got in first case. Equation number 1 implies that equation number 1, E is equal to 1 by 4. There we had got 1 by 4 pi epsilon naught Q by r square. That is what we had got, right? Now replace this Q by this value of Q, right? Okay, so what we will get, 1 by 4 pi epsilon naught. Now here we will get rho into 4 by 3 pi small r cube by small r square. So here you can see clearly small r square cancels small r cube to give r only, and pi gone, 4 gone. That is why here we will get E is equal to 1 by 3 into rho by epsilon naught into r into small r. That is what we will get for what, small r less than capital R. Okay, this is the electric field at P due to the sphere. Sphere, right? So hope you have understood this. So now you see in the next video we're gonna discuss about electric field intensity or electric field at a point due to a uniformly charged infinite set. Okay, so in that case also how to apply the Gauss law to find the electric field. We're going to discuss that in the next lecture. So hope you have understood this, and if you have understood, please share with your friends and hit the thumbs up button. Also subscribe the channel if you haven't subscribed the channel yet, and also share with your friends, and also hit the bell icon so that you get notified when new video will be uploaded. So thank you for watching. See you in the next video.